Welcome to the first session of our professional development series. We are kicking off day 1 of our Introduction to Petroleum Reservoir and Geology e-learning program. As we begin this journey together today, our primary objective is to build a rock-solid foundation for understanding the subsurface environments that house the world's energy resources. To do that, we must start at the very beginning of the geological story. Module 1. The Rock Cycle. Our first module focuses on the rock cycle. Before we can analyze complex reservoir architectures, we have to understand the life cycle of the rocks themselves, how they are formed, weathered, and eventually transformed into the reservoirs we target. Throughout this module, we will explore fundamental rock types, distinguishing between clastic and non-clastic reservoir rocks, depositional environments, how the specific setting where a rock is deposited, whether it's a river, a delta, or a reef, dictates its pore volume and flow properties. Porosity and geometry. Why the type of porosity is a direct result of its environment, and how that environment ultimately shapes the physical geometry of the reservoir we must model. By the time we reach the end of Module 1, you will have a clear understanding of how these geological processes create the internal and external properties of a successful reservoir. Let's dive into our first look at the processes that shape the Earth's crust. Let's take a moment to understand just how our planet is built, because it's pretty remarkable. The Earth, as you might know, has a diameter of about 12,750 kilometers. The ancient Greeks were actually the first to estimate that, using shadows and geometry. But it wasn't until the early 20th century that scientists really began to understand that the Earth isn't uniform. It's layered. You can think of it almost like a boiled egg. We have 3 main layers: the crust, the mantle, and the core. Now, the crust is the outermost layer. It's what we live on, and compared to the rest of the Earth, it's incredibly thin. Under the oceans, the crust is usually about 5 kilometers thick, and beneath continents, it averages around 30 kilometers. But here's what's fascinating. Beneath large mountain ranges like the Alps or the Sierra Nevada, the crust can go as deep as 100 kilometers. Imagine that. Just like an eggshell, Earth's crust is brittle. It can crack and break, which is exactly what happens during earthquakes. When we look at cutaway diagrams of the Earth, especially ones drawn to scale, it really drives home how incredibly thin that outer shell is. Just skin deep. The vast majority of Earth's volume lies beneath, in the mantle and the core. The mantle, which sits right below the crust, is much thicker and more dynamic, and the core, well, that's a whole world of molten and solid metal all on its own. Understanding these layers is key to unlocking not just how the Earth functions geologically, but also how resources like oil, gas, and minerals are formed and move. Now let's take a deep dive into one of the most fundamental concepts in geology: the rock cycle. This concept, first proposed nearly 2 centuries ago by James Hutton, the father of modern geoscience, shows us how rocks are constantly being transformed from one type into another over geologic time. Picture the Earth's upper layers, its crust and mantle, as part of an enormous recycling machine. No matter is lost. Instead, rocks are broken down, reformed, and reborn again and again. At the surface, all rocks, whether igneous, sedimentary, or metamorphic, are subject to weathering, a process that breaks them down into sediments. These sediments are then transported, deposited, and buried, and over time, through lithification, a process of compaction and cementation, they become sedimentary rocks. But the story doesn't stop there. If these rocks are buried deeper, where temperatures and pressures are much higher, they undergo metamorphism, becoming metamorphic rocks. And if that burial goes even deeper still, the rock can actually begin to melt, forming magma. When this magma cools, either below the surface or after erupting from a volcano, it crystallizes to form igneous rocks, starting the cycle all over again. What's fascinating is that any rock type, igneous, sedimentary, or metamorphic, can be transformed into another through these 4 key processes: weathering, crystallization, lithification, and metamorphism. And don't forget the role of tectonic processes in all of this. They're the driving force, pushing rocks upward to be weathered or downward to be transformed. So the rock you hold in your hand today might have once been lava flowing out of a volcano or part of a mountain range that's long since eroded away. That's the magic of the rock cycle. Endlessly dynamic, interconnected, and foundational to understanding how our planet works. And as future geoscientists or engineers, knowing how these rocks behave and transform is critical, because the story of hydrocarbons, reservoirs, and Earth's structure begins right here. Now, let's talk about the three major rock types: sedimentary, igneous, and metamorphic, and why understanding them is so important, especially in the context of petroleum geology. These rock types are classified based on their origins, meaning how they were formed. First, we have sedimentary rocks, which are incredibly important for oil and gas exploration. These rocks are formed from particles, tiny bits and fragments, that come from the breakdown of other rocks, including igneous, metamorphic, or even older sedimentary rocks. These particles are transported, deposited, and eventually compacted and cemented over time. Sedimentary rocks are where we find both hydrocarbon source rocks, those rich in organic matter that generate oil and gas, and reservoir rocks, which store and transmit those fluids. Then we have igneous rocks, which form from molten material, or magma. If this molten rock erupts at the surface, we get things like lava flows and volcanic ash. If it cools slowly beneath the surface, we get coarse-grained rocks like granite. Now, igneous rocks aren't the main players in hydrocarbon exploration, but in rare cases, we can produce hydrocarbons from fractured igneous rocks, if they're naturally porous or cracked. Lastly, we come to metamorphic rocks. These form when any existing rock, whether it started as igneous, sedimentary, or even another metamorphic rock, is subjected to high temperatures and pressures. This process transforms the rock's structure and composition. Examples include marble, which comes from limestone, and slate, which comes from shale. But here's the key point. Due to the intense conditions involved in metamorphism, most of the original organic material is lost, making these rocks poor candidates for oil and gas reservoirs. So in summary, while all three rock types are part of the Earth's dynamic system, sedimentary rocks are by far the most important for us in petroleum geology. 4 main types of igneous rock. Now let's take a closer look at some of the main types of igneous rocks. Because even though they're not the primary source of hydrocarbons, they tell us a lot about the Earth's interior and can occasionally host reservoirs in fractured zones. First up, we have basalt. Basalt is one of the most common rocks on Earth, and it forms at mid-ocean ridge volcanoes, places where tectonic plates are pulling apart and magma rises to fill the gap. It cools quickly at the surface, which gives it its fine-grained texture. Basalt is typically very dark in color, almost black, and its crystals are so small you often can't even see them with the naked eye. It's what you'd see making up the ocean floor. Next, we have gabbro. Unlike basalt, gabbro forms deep within the Earth's crust. It's made from similar mantle material, but since it cools slowly underground, it develops much larger, coarser crystals. Gabbro is also dark-colored, like the salt, but you'll notice a much more granular, speckled appearance. You could think of it as the underground cousin of basalt. Same ingredients, different kitchen. Now let's shift to the lighter end of the spectrum with rhyolite. Rhyolite is also a fine-grained volcanic rock, but what sets it apart is its high silica content. That silica gives rhyolite a much paler color, often light gray, pink, or even white. It also forms at the surface, typically in more explosive volcanic environments, where rapid cooling traps in gases and creates a lighter, sometimes porous rock texture. And finally, we have granite, a rock many of us are already familiar with from countertops, but geologically, it's fascinating. Granite is an intrusive igneous rock, meaning it crystallized slowly beneath the Earth's surface. Because of this slow cooling, granite has a coarse texture with large, visible crystals. Like rhyolite, it's rich in silica, which gives it its light color, often a mix of white, pink, or light gray, with speckles of quartz and feldspar. So, to recap, basalt and gabbro are the darker, low-silica rocks, basalt forming quickly at the surface, gabbro forming slowly at depth. Meanwhile, rhyolite and granite are the lighter, high-silica rocks. Again, rhyolite cooling quickly above ground, and granite cooling slowly underground. Understanding these variations is key, not only for identifying rock origins, but also for assessing their potential, however rare, as fractured hydrocarbon reservoirs or as seals and barriers in the subsurface. Let's explore some of the most recognizable and geologically significant metamorphic rocks, each with its own story of transformation under intense heat and pressure. We'll start with gneiss. Gneiss typically forms from an igneous parent rock, like granite, that has been subjected to high-grade metamorphism. One of its most distinct features is its banded appearance. Light and dark minerals segregate into layers as a result of both melting and pressure. These bands often align in the direction of maximum pressure, making gneiss not only visually striking, but also a clear indicator of tectonic forces at work deep within the crust. Next up is mica schist, another rock that tells a story of intense pressure. The term schist refers to the parallel arrangement of minerals, and in mica schist, mica is the dominant mineral. These rocks tend to be coarse-grained and have a shiny, glittery appearance due to the presence of minerals like biotite or muscovite. Mica schists often form from shale or other fine-grained sedimentary rocks and are typically found in regions that have undergone deep burial and deformation. Now let's talk about slate. Slate is one of the most well-known metamorphic rocks because of its everyday use, in roofing tiles, blackboards, and even flooring. It forms from shale, a sedimentary rock, and is known for being highly foliated, meaning it splits cleanly along flat plains. Slate is usually dark in color, fine-grained, and forms under relatively low-grade metamorphic conditions. It's an excellent example of how pressure can realign minerals to produce clean, predictable planes of weakness. Then we have marble, which is not only a geological marvel, but also a cultural icon used in sculptures and architecture. Marble forms from the metamorphism of limestone, which is mostly composed of calcium carbonate. During metamorphism, the calcite crystals recrystallize, removing any fossil content and giving marble its classic smooth appearance. Depending on the impurities present, marble can be white, pink, green, or even black. It's a fantastic example of how a relatively soft rock can be transformed into a durable, beautiful material under heat and pressure. Lastly, let's look at quartzite. Quartzite is the metamorphic equivalent of sandstone and is composed almost entirely of silica, SiO2. It forms when sandstone is buried deep in the earth and subjected to heat and pressure, which fuses the quartz grains together into a dense, hard rock. Quartzite is extremely resistant to weathering, making it a popular choice for construction. It can be mistaken for marble at times, but it lacks calcite and won't fizz in acid, a good trick for geologists in the field. Each of these rocks, gneiss, mica schist, slate, marble, and quartzite, illustrates the incredible diversity of outcomes possible when rocks are subjected to Earth's internal forces. And understanding their formation helps us read the geological history of the regions they come from. Now let's talk about sedimentary rocks, which are without question the most important rock type when it comes to petroleum geology. These rocks are where we find almost all hydrocarbon reservoirs, most source rocks, and the essential cap rocks that trap oil and gas in place. Sedimentary rocks form at the Earth's surface through the accumulation and compaction of sediments, and they're typically divided into two broad categories: clastic and non-clastic. Let's start with clastic rocks, which include familiar names like sandstones, shales, and silts. These rocks are made primarily of silicate minerals, especially quartz, SiO2, and they're classified based on two main factors: mineral composition and grain size. Clastic sedimentary rocks are essentially fragments of older rocks that have been broken down by erosion, carried away by transportation, usually via water, wind, or ice, and then laid down through deposition. Over time, these loose sediments are compacted and cemented together to form solid rock. Sandstones, for example, are key reservoir rocks because of their porosity and permeability, while shales are often the source rocks, rich in organic material. Understanding the grain size and sorting of these rocks is crucial because it directly impacts how fluids, like oil and gas, move through them. Now let's move on to non-clastic sedimentary rocks, which include carbonates and evaporites. These rocks don't come from the breakdown of older rocks, but instead form through chemical or biological processes. Carbonates, like limestone and dolomite, often form in warm, shallow marine environments where organisms like corals, algae, and shellfish thrive. When these organisms die, their calcium-rich remains settle to the bottom and eventually form rock. These biologically derived carbonates can create incredibly effective reservoir rocks, especially when they undergo processes like dolomitization or fracturing. Then there are evaporites, such as halite, rock salt, and gypsum, which form when water bodies evaporate, leaving behind minerals that crystallize and accumulate. While evaporites aren't typically reservoirs themselves, they often serve as excellent cap rocks, providing a tight seal that traps hydrocarbons in place. So to recap, clastic rocks come from broken-down fragments and are mechanically deposited, while non-clastic rocks are formed chemically or biologically. Both types are critically important to the petroleum industry, but in very different ways. Clastics give us many of our best reservoirs and source rocks, and non-clastics, particularly carbonates, provide both reservoirs and structural complexity that can make or break a hydrocarbon system. Let's now look at a few specific sedimentary rock types, each with unique features that tell us something about their environment of formation and their relevance to petroleum geology. We'll start with breccia. Breccia is a rock composed of assorted, angular fragments that haven't traveled very far from their source. Because there's little to no transportation, the edges of the rock fragments stay sharp and jagged. Breccias often form in collapsed structures, like caves or karst systems where limestone has dissolved, or along fault plains, where rock has been broken up by tectonic movement. Breccia doesn't typically serve as a reservoir rock, but its presence can tell geologists a lot about structural activity in an area. Next, we have conglomerate. Conglomerates look somewhat similar to breccias at first glance, but the difference is in the shape of the fragments. In conglomerates, the clasts, usually pebbles and rounded stones, are well-rounded, which means they've been transported over some distance by water or other natural forces. This rounding tells us the environment was high energy, such as beaches, river channels, or nearshore marine zones. Conglomerates can be important in petroleum geology because the larger grain sizes often mean good porosity and permeability. Now, let's talk about sandstone, probably the most important sedimentary rock when it comes to reservoir quality. Sandstones are made of well-sorted quartz grains, usually deposited in deserts, deltas, or shallow marine environments. What makes sandstone such a strong candidate for oil and gas reservoirs is its porosity and permeability. It can store hydrocarbons and allow them to flow relatively easily. Clean, mature sandstones with minimal clay content are particularly valuable in the subsurface. And finally, we come to shale. Shale is a dark-colored, very fine-grained sedimentary rock, often heavy and compact. It forms in low-energy environments, typically deep sea or deep marine basins, where tiny clay and organic particles slowly settle out of the water. Shale is typically low in permeability and porosity, which makes it a poor reservoir but an excellent cap rock. In fact, it often acts as both the source rock, rich in organic material that generates hydrocarbons, and the seal, keeping those hydrocarbons trapped in the reservoir below. This dual role makes shale one of the most important rocks in the petroleum system. So breccia tells us about structural disturbance, conglomerate reflects high-energy transport, Sandstone offers high reservoir potential, and shale plays a critical role in both sourcing and sealing hydrocarbons. Understanding these rock types helps us read the geological record and identify potential oil and gas systems. Let's now dig deeper into clastic sedimentary rocks, which play a central role in petroleum systems. Clastic rocks are made up of broken fragments of pre-existing rocks, and the key difference between the types of clastic rocks lies in one simple factor: grain size. At one end of the spectrum, we have sands, which are made up of larger, coarser grains, usually quartz. And these sands, when compacted and cemented over time, form sandstones, which are among the most important reservoir rocks in the oil and gas industry. They typically have good porosity and permeability, which means they can both store hydrocarbons and allow them to flow. On the finer side of the grain size scale, we have shales and silts. These are much more fine-grained, so fine, in fact, that fluids trapped inside them can only move out incredibly slowly, over geological time. That's why shales are so often our source rocks. They're rich in organic material and generate hydrocarbons when subjected to heat and pressure during burial. But they don't easily allow those fluids to escape. In some cases, shales also act as cap rocks, effectively sealing hydrocarbons within the underlying reservoir. Silts sit in the middle, grain size-wise, and like shales, can be quite tight, with limited permeability. One more important point: clastic sediments can come from any type of rock: igneous, metamorphic, or sedimentary. They're weathered, eroded, transported, and eventually deposited, often in layers, before being buried and transformed into solid rock. And while they start off saturated with formation water, it's the migration of hydrocarbons into these pore spaces that turns a simple sediment into a working petroleum reservoir. So, in essence, clastic rocks, especially sands, silts, and shales, are foundational to our understanding of where oil and gas are sourced, stored, and sealed. We said clastic rocks are sands, silts, and shales. The difference is in the size of the grains. Let's take a closer look at the classification of clastic sedimentary rocks based on grain size, because this is one of the most important tools we have for understanding their properties and how they behave as reservoir, source, or seal rocks in petroleum systems. We'll start with the finest grained of all, shale. Shale is made up of particles that are smaller than 0.004 millimeters. So small, in fact, that individual grains can't be seen with the naked eye. These tiny particles settle out of suspension in very low-energy environments, like deep marine basins or lake bottoms. Because of this fine grain size, shales have extremely low permeability, making them excellent cap rocks. And they're often rich in organic matter, which makes them the most common source rocks in hydrocarbon systems. Next, we have siltstone, which bridges the gap between shale and sandstone. The grain size for siltstone falls between 0.004 millimeters and 0.06 millimeters. Siltstones form at slightly more energetic environments than shales. Think floodplains or deltas, but they're still considered tight formations with relatively poor fluid flow. In the petroleum context, they're usually non-reservoirs, but they can play a supporting role as part of a larger stratigraphic sequence. Then we move to sandstone, which has a grain size ranging from 0.06 millimeters to 0.2 millimeters. This is where things get interesting for reservoir development. Sandstones are typically well sorted and composed of quartz grains, that's silicon dioxide, or SiO2. These rocks are formed in moderate to high energy environments, like deserts, beaches, or shallow marine settings. Because of their grain size and mineralogy, sandstones often have good porosity and permeability, making them the primary reservoir rocks in many conventional petroleum systems. Finally, we come to the coarsest clastic rocks, conglomerates and breccias, with grain sizes ranging from 2 millimeters to 256 millimeters. These rocks are made up of larger fragments, pebbles, cobbles, or angular clasts. Conglomerates have rounded grains, which suggests they've been transported by water over some distance, while breccias are composed of angular fragments, meaning little transport and high-energy deposition close to the source. While these rocks are less common as reservoirs, they can sometimes serve as hydrocarbon-bearing formations if there's enough connected pore space, especially in fractured or tectonically active zones. So, to summarize, grain size tells us not only about the environment of deposition, but also about a rock's fluid flow potential. From shale as a source and seal to sandstone as the ideal reservoir, each clastic rock type plays a unique and valuable role in petroleum geology. Now let's move into the world of non-clastic sedimentary rocks, particularly those that play critical roles in petroleum systems. We'll start with limestone and dolomite, which are two of the most significant carbonate reservoir rocks. Limestones are primarily composed of calcium carbonate, and they often form in shallow, warm marine environments, places where organisms like corals, algae, and shellfish thrive. While some limestones are naturally porous, others are very dense and have low primary porosity. However, there's an important geological process called dolomitization, which can dramatically improve a rock's reservoir quality. Dolomitization occurs when limestone is chemically altered by magnesium-rich fluids, transforming it into dolomite. This not only increases porosity, but also enhances permeability, creating vital fluid pathways. That's why dolomitization is such a key mechanism in many carbonate reservoirs. It transforms what might have been a tight rock into a productive reservoir. Next, let's look at chalk. Chalk is a fine-grained, soft variety of limestone, made mostly of microscopic plankton shells called coccoliths. What's unique about chalk is that it can have very high porosity, meaning lots of pore space for fluids, but that doesn't mean it's a great reservoir by default. Why? Because its permeability is often extremely low. The pore spaces in chalk are not well connected, so fluids like oil or gas have a hard time flowing through it unless it's fractured. Some successful chalk reservoirs, like those in the North Sea, work only because of natural or induced fractures that provide the needed permeability. And finally, let's talk about evaporites, which are rocks that form when water evaporates and leaves behind minerals like halite, rock salt, and gypsum. While evaporites are not reservoir rocks themselves, they're extremely important in the overall petroleum system because they make excellent cap rocks. Their very low permeability means they can trap hydrocarbons beneath them, acting like a tight seal that prevents oil and gas from migrating upward. In fact, some of the world's biggest oil and gas fields are sealed by thick beds of evaporite. So, to sum it up, limestones and dolomites can be excellent reservoirs, especially when altered by dolomitization. Chalk can store fluids well, but often needs fractures to produce. And evaporites, while not reservoirs themselves, are essential as reliable and effective cap rocks that help trap hydrocarbons in place.